On Wednesday, we were discussing support vector machines. Any questions here or in Florida about the basic concepts? We'll go, again, once we're done going through all of this, we'll go back to Weka and see how we can implement things within Weka. Support vector machines might be a little tricky because you have to make sure that the libsvm is installed, or we can just do that separately. So, any questions here in Alamosa? Not yet? What about in Daytona Beach? So in Daytona Beach, you should have gotten your homework back. Everyone get their homework back? Okay. No questions? No. None. Okay. So we're going to switch topics. We finished support vector machines. There's a couple more methods we're going to look at for classification. And the next one is artificial neural networks. And then we'll follow that up. We might start today a little bit, but we'll definitely follow up with what are called ensemble methods on Monday, and that'll pretty much then finish the whole module on classification. And then after that, we'll have our first quiz. So I'll bring up artificial neural networks, and I think I just go. Okay. So, artificial neural networks, we're going to talk about, first of all, what they are and where they came from. And in essence, they're inspired by neurons in the brain. So neuroscience of the brain. And in the brain, you can think of, and I'll have a picture here coming up, but you've got neurons, and they're basically connected to each other by strands of fiber. And the basic idea is that these axons, the strands, will transmit impulses or, between the neurons. And basically what happens is they're going to be all connected up, and there's multiple types of neural networks, but they're going to, a neuron can send impulses to other neurons. So if you look at a single neuron, it'll be connected to multiple neurons that can then send impulses to it. And then if those neurons that come into if the impulses that come into a neuron are at a high enough signal, then that neuron will fire. And when that neuron fires, it can transmit impulses to other neurons. So that's, in a sense, that's the basic idea underlying a neural network. The dendrites connect neurons to axons, and basically what happens is the learning will happen through changes in these strengths of these connections between the individual neurons. We'll go through some examples as we go through it. Here's kind of an overview of a simple neural network. This is an example of a feed-forward neural network, in that you've got inputs on one side, and your output's on the other side. And in this example, it actually has what's called a hidden layer, which is where some of the calculations are going on. There are different types of neural networks, and we'll discuss that. Questions so far before we begin? So you can think of these nodes, these circles, as the neurons, and these arrows, in this case it's directed. Not all of them are directed, but these are the connections between the neurons. So we're going to back up a little bit to kind of the beginnings of neural networks. And the very first type of neural network, it was invented at Cornell Aeronautical Laboratory by a man by the name of Frank Rosenblatt. It was a very simple neural network. It was called a perceptron. I can actually, the idea here, it was a single layer feed-forward neural network. What that really means, I'll actually try drawing it here. If I can get, does this have shapes? Mm-hmm. Star. I'm looking for like a circle.
Up the box, down that.
There we go. So if you think of this, let's see, how do I want to draw this? And basically it was just a single layer. So this could be our output, and basically it's just a single layer. So here would be, over here would be our inputs. So this could be an input, say, right, you could have an input here, an X1 attribute, that didn't come out too well. So now you can have all these different inputs here. So this would be an example of a very simple with 3 different inputs. And then it goes to this circle, which then has your function, and it just combines those inputs, and it's going to have an output. So that's a very simple version of a neural network. Single layer, one layer versus multiple layers, as in the previous examples. Where were we? So that was way back in 1957. It looked promising initially, but it ultimately was disappointing. It was only able to learn very simple, linearly separable patterns versus some of the more complex ones. For example, we even looked at in support vector machines, even though we looked at linear separations, we were able to use the kernel trick to get many different shapes. This was later extended by professors Marvin Minsky at MIT and Seymour Papert, and they started investigating multi-layers, and that's where you start getting those hidden layers, perceptrons. So here it is. It's the original perceptron was an algorithm for learning binary classification, similar to SVMs. It maps the inputs x to the output f of x, which is 1 or 0s. And you can begin to see some similarities here with support vector machines in the form of the actual function. The weights dotted with the vector, and notice the linearity there. More generally, since then it kind of died off for a while, and then it started being reinvigorated later on. And now there are many different types of artificial neural networks. And the basic types, we've seen an example, feed forward. Basically, the main difference here with the feed forward artificial network is there's no directed cycles. So you can't, it doesn't go, is that, you giving me a quizzical look?
No, I understand. It only goes one direction.
It only goes one direction. You're not going to get a circle happening. There's no basically feedback mechanism. An example of that is the multi-layer perceptron. Recurrent neural networks, these can have directed cycles. So now you can start to feed back onto, a neuron can feed into another neuron, and end up coming back to the original one. The recurrent neural networks are often used in handwriting recognition. And I'm going to actually discuss recurrent neural networks, then breaks down even further into even more multiple types. You can have fully recurrent systems, or an example, I bring this up, long short-term memory. This was championed a lot by a researcher, Jürgen Schmidhuber at the Swiss AI Institute, IDSIA in Lugano. And his mechanisms of long short-term memory, coupled with some recurrent networks, one, I think from 2009 to 2012, there's some international competition for handwriting recognition, and for those years, his team won that recognition. And he also employed a little bit of some what are called some deep learning neural networks as well in that, which we'll talk again briefly about. Some other types of recurrent neural networks, Hopfield networks, which were designed by John Hopfield in 1982. So these all have symmetric connections. So if you've got two neurons, you've got a single weight between them, and they can go in both directions with that same weight. So if neuron A is connected to neuron B with weight 1/2, it's the same weight from B going to A. And these can model in, also, you can model then those weights as a matrix. So you have all your neurons listed on your rows as well as on your columns. And what that would then mean is you have a symmetric matrix. The transpose of the matrix is equal to itself.
When they're at 50.
Regardless of what the values are, right? If your ij element is p, then so is your ji element. So it's going to be, if you reflect it about the diagonal, it's going to look exactly the same. It's symmetric. So one of the nice things about the Hopfield networks, and you notice I also put in there ECANs, which stands for Economic Attention Networks. That's some work that I've actually done with the OpenCog team in Hong Kong. It's based on the same ideas. One of the really nice features of the hot field network is it's what's called an attractor network. What that means is that the dynamics internally are guaranteed to converge. And so one of the strengths here in terms of handwriting or character recognition is, so I'll bring up the whiteboard again here. If I can. So say you've designed it for, say, the number 4. Right? Well, so, and that's what you think of, the computer thinks of as a number 4. But Pablo comes along and he writes it as that 4, right? It's not quite, it doesn't match up. So there's some, basically the idea here is why it can be used pretty cleanly with handwriting recognition is we can fuzz up our initial 4 and the neural network will still converge. So the version of 4 on the right will converge to that 4. Versus another set of examples, if we have the number 5, which we can think of as looking like that, will be in a different, what's called basin of attraction. I can be far enough away from that 5 and the neural network will still identify it as a 5 versus a 4. But in a different basin of an attraction, everything in that region will all converge to the 4. Does that make some sense? That's what I mean by the dynamics converges.
Okay.
Yes? No?
Yeah, sure.
See.
Okay.
That's it.
And one of the other advantages, one of the nice things about hot field networks, they can also, and this is part of it, they can serve as a memory, an associative memory, and store those shapes. And then anything nearby will converge to those. And that kind of brings us a little bit more modern. These are more recent neural networks or deep learning architectures. Originally, kind of, probably the forerunner of these in some ways would be hierarchical temporal memory. Jeff Hawkins, I don't know if you are young enough to remember Palm Pilot.
Oh, yes. I love Palm Pilot.
I love Palm Pilot.
So that was invented by Jeff Hawkins.
Someone stole mine in 7th grade.
So, and then he went on and he started a company. It was originally called Numenta. They've since gone in different directions. He formed a company with Dilip George to pursue this model of hierarchical temporal memory. Dilip George now owns a company in Silicon Valley called Vicarious Systems. And they're now pursuing different directions, but they're in the same ideas. There's also some concepts called deep belief networks that were championed by George Hinton. And then convolutional networks introduced by a couple of other individuals. Yann LeCun, who is now works at New York University and is also director of research of AI research at Facebook. And Yoshua Bengio, there's a link to a book, preprint of a book on the website that he's writing on some deep neural networks. And this is kind of the forefront of what's happening right now in terms of neural networks. Another one I mentioned because it's something I've actually worked with myself, but Itamar Errol invented deep spatiotemporal inference networks, or DESTIN for short. And Google DeepMind was a company originally founded in London by a few individuals. And it was recently purchased. They're basically looking at gaming and having the computer play, old Atari games, and using some deep learning principles on that.
Like have it learned from.
And it was recently just purchased. This year it was it this year? It was purchased by Google.
Didn't we do something with that in Dogland and Sin?
Yeah.
Right? It was like,
So that's kind of more state of the art. Within so there's a few processes we need to work with here, right? So you've got these neural networks and you have to train them. And so there's different ways of training them. And what does training mean in the context of neural networks? Means what should the appropriate weights be? So you're going to train them you're going to adjust the weights. And so you can do this either in a supervised fashion in which you infer the mapping from your training data. And typically here you use what's called gradient descent method, which actually it's gradient descent and the neural networks that leads to an algorithm called backpropagation. Basic idea of gradient descent. Who's heard that before? Pablo, you raised your hand.
Sure.
Oh.
I've read that.
yeah.
Calc 3.
Calc 3, what does that mean?
It's the fastest way down.
Right, you're basically going to look where you are and see what's the
Quickest way
down to a minimum.
Isn't that just the gradient?
That's
We're doing the gradient.
gradient descent.
So it's the same thing, it's just
Right.
the gradient.
Right.
I like the gradient.
You can also do unsupervised learning, which you have in the background some given cost/energy function, and now you want to minimize the cost, or you want to minimize the energy function. So you think of, and the energy that's more physics principles. You've got your energy, and you want to minimize the energy in your system. So you can come up with what does that mean. You can also use a concept known as reinforcement learning, where you have you're an agent, you're interacting with your environment, you're collecting data, you're making decisions, and you start looking at the results of your decisions. How does that affect your accumulated costs? And then you're going to adjust your actions. So I'm not going in there. In other words, this is a huge area, artificial neural networks. There are many different forms. Characteristics, a lot depends on the choice of the model. And the choice of the model, like all data mining, depends upon the application that you're looking at. Complex models, one of the drawbacks of a really complex model tends to be they're more difficult to learn. If you have a fully connected model, that's a lot of weights. The learning algorithm that you're going to use may require considerable experimentation, to design the appropriate cost function, but also for parameter adjustments. the choice of the threshold function can also affect your results. So the threshold function is how do you, that's the function that decides when the accumulated inputs to a neuron will result in that neuron firing and spreading the activation further along the chain. So, you can choose different threshold functions, either a strict threshold value, or you can adjust it using something like an inverse tangent function curve. So it's kind of a sigmoid curve, so it has a little more shape to it. So it's not just a either or, but it starts to get really, really close and then fire. So it's not quite as hard a decision. They can be robust. One big advantage of neural networks is it's very easy to implement these in parallel. Because you can think of each individual processor as a separate neuron. So that makes it very easy to implement this in parallel. And some exciting things going on in the actual world of chip development, so computer processor developments, is an area called neuromorphic computing. IBM recently has been working on what they call neuromorphic chips, which are basically chips designed with neural networks in mind. So they basically are going to do neural networking themselves. So which brings us, so I'll back off here, and before we move on, brings us to the next module, or next section in this module, ensemble methods. Talk to me, how did neural networks, does that seem clear, or James?
I don't know. I mean,
What would be an example of a neural network?
What do you mean by what would be an example?
Tell me how it's used today.
Yes.
Besides the handwriting recognition example, I mean,
Is voice recognition something like that too?
it's used in, I mean, it is being used in image
Is
recognition.
it like fingerprint, like stuff like that?
Yeah.
I can't say per se, because I don't know exactly about that example. I do know it is being used in image recognition.
Okay.
More, and so I mean, more right now, it's these deep learning methods. And so let's back up to there. So you bring some good questions.
So you say there's a chance.
So I probably didn't, so what do I mean by deep learning architectures in the context of neural networks? Because there's deep learning architectures are not restricted to just neural networks, but that's where most of the research has gone on in, say, the last 5 years. So what we mean here is, I should probably have brought up a, I don't know if I had a picture. Let's go back to this picture here. And this is an example of a single layer network. So what a deep learning network would mean is, instead of having this single intermediate layer, you're going to have many different layers. And I'll talk about it a little bit more in terms of what I know, which is more in terms of the Destin architecture. And let's see if I can't draw, but let's try it anyway. Right? Okay, so you've got these different layers. So let's see if I can can I draw a tilted box?
They doesn't look like
No.
it. Unless you can click on the box after you've done.
You know, what I'm thinking is
Go to paint.
I'm going to share the desktop. And I'll bring up Word, right? And so let's see. Insert shapes. Can I do, I should be able to do 3D here. I just kind of, can I rotate that in 3 dimensions?
Yeah, not in 3 and 2.
And 2. Well, let's just do lines. Because I can draw, so here might be, pardon?
There was a 3D box in there.
Oh, there was?
Yeah.
Where?
Shapes.
Shapes?
Down.
Under basic shapes.
Under basic shapes. Over to
Second
the
row, far right.
left. I mean right.
I see.
Sorry.
Right.
Right. Up.
Two,
Up.
down a little.
Down.
Down, no, no.
Down, down.
Down.
Right, oh,
Down one more.
Oh, here they are.
Yeah.
Those are cubes.
You look like
There's
dad
a
do,
few.
Peter.
If you stretch it out, you might.
You
be
can
able
do, yeah.
to see.
I'm just trying to get a perspective. I'll just draw it.
Okay.
Joke, hey.
Nice try, right? So what I'm after is kind of like, and unfortunately it doesn't do the nice color I want. So this is always a pain on the computer. Is the smart board working?
Yeah.
Yes, it is.
Should we try that?
Let's try it.
Do it.
It's not working.
Stupid thing.
Do I need to spread? No, I need to do that. There we go. Right, so there's a layer, okay?
Okay.
And you can think here of having some pixels. So maybe you have a whole bunch of pixels here that it's not all agreeing with the same location as I'm drawing.
I just need to do the calibration, take the 2 buttons there, just hit them.
Which 2 buttons?
The 2 buttons on the front. No,
Yeah.
yeah, there you go. No, see the little
Target.
top left? No.
Up.
Top left, you gotta hit the little corner. You gotta do all 9 of them, I think there are. Maybe 12.
It's a game.
A smart board. It's so sleepy.
That's if it.
Okay. So let's try that again. Here's a bunch of different pixels. And I'm trying to draw it as like a group.
Okay.
So then what's going to happen is we're going to have another layer, say up here. And in Dessin you get these things called centroids, but the more basic idea is you're going to aggregate, think of this as a single, you're going to aggregate that as a single pixel on, say, the layer above. So then it becomes, all of this gets mapped into, say, a single point on the next layer.
So kind of like the transformation.
And then what's going to happen as well is now you might have another layer up here, and it's out of sync again, right? And what's gonna happen here is you're gonna again get a group of these that come from a larger, so this one, you know, this one here is coming from another group of cells down here. Right? So all of this is getting to another one, and then all of these in turn get translated into one of these up here.
So you're taking all the data and kind of compacting it.
And so if you notice this, so think of that hierarchical concept that I mentioned with Jeff Hawkins, with hierarchical temporal memory. And you notice this hierarchical system here as well.
So
it's kind of transferring from layer to layer to layer up. And by deep learning, you have multiple layers instead of the original ones, which were very simplistic. Yes?
So the further down you go, the more information.
Right. I mean, so you think of a visual system. So it's aggregating, it's processing, it's aggregating, it's processing, and it's moving up the line. And these sorts of systems, and there's all kinds of different sorts, convolutional networks and so on, have led to quite dramatic breakthroughs in image classification. And that's the example where recently Google came out with a press release saying, look, our system spontaneously identified a picture of a cat. So, and it's based on these kinds of...
cat pictures?
Pardon?
You didn't show it cat pictures?
I didn't follow through all of the details on that. But
if you had to train
So-
it, you didn't have to know what a cat looks like?
let's see. I'm gonna click out of here. And with that, give access. And questions? Did that answer your question, James? Huh?
Yeah, hey, we're here.
Questions?
Yeah, I have a comment. Actually, what you're talking about, the deep learning, is associated with the project in my mind, and we'll try to do in this couple of years. When you do the layers, now we have a problem in our mind. Start from the satellite image. The satellite image have a very low resolution. 1 pixel is about 30. That's called the Landsat.
Mm-hmm.
Can you hear me?
Yes, I hear you.
Okay. Then the next layer, we try to find some middle layer, get the picture from the or airplane or weather balloon.
Right?
That will be thousands times of higher resolution, but the data size will be thousands times bigger either.
Right?
And then the next layer, we're going to do the water, try to find the seagrass. And that time, the resolution is another thousands times higher, but the data size is another thousand times bigger. But now we talk about a physicing, because we have the balance with a very high resolution, very huge data we cannot treat, but the compensated by the very low resolution, but the small data size.
Right.
And then we try to find the seagrass and the sea turtle, dolphin, manage by merge all those images. Just kind of like the picture you're drawing. 3 layers, you could have 4 layers.
Right, multi-scale is what it sounds.
Yeah, just let you know the size of our data.
Right.
If you real data for this analytical like Google, I would calculate 100 tera. Just like Google Earth, for the very low resolution, kind of 100 terabytes. We try to zoom it down to 100 meg. basically as a map site stamp. It's very interesting doing the research on this layer to see how we can use all this data and use the high resolution to give some sporadic information for the low resolution and the low down to give some information.
Right.
It itself is a very good research problem.
Yeah, no, that's, I see the different, I mean, I see that as a different scales. You have lots of different scales.
Yeah.
Multi-scales and information at different levels of resolution.
Yeah, it's all about the money.
Right.
Because the data at the level is very expensive.
I remember reading something on combining different different scales in some of the work I've done, and it works in both ways. Different time. That example was different time scales, but it could. I think it also worked on different spatial scales, and you can work it both ways. The finer resolution can help you update your coarser resolution and vice versa.